that the estimate is that there is about 1 gamma ray burst per day.
Okay.
The point is that they have different quality of observation. So there are a few events where you only see the burst as the trigger is triggered, and that's it. There are other cases where you can see an afterglow, where you can follow the front of emission, and so on and so forth. In general, good ones are not very common.
Are there any worries that there's some other object which is masquerading as gamma ray burst?
Yes, but this is a good point. These things here tell you that there can be that many, right? So it cannot be a galactic object, otherwise there will be an overdensity over the galactic plane. It's also ruled out local object because there is absolutely no overdensity toward the Virgo cluster. And in principle, one might assume there are very localized objects, like the galactic halo or something like that. But there are measured redshift. So, and then none of them is coincident with what we get here. So this is essentially the redshift distribution. They are concentrated between redshift 2 and 4, essentially. And this is the typical isotropic energy sensitivity.
And if they were just uniformly distributed in time, which redshift would we see them peak at?
If they were uniformly distributed in time?
In time over the age of the universe.
You will say uniform distribution, right? Which you don't.
Well, no, because different z's mean different radii.
Ah, okay. Yes, yes,
like
yes.
Z squared effect there.
There is a 1 over z squared, but ultimately there is very little at between 1 and 2. There are various other indicators of this. So the point here is that they divide into groups. Okay, so this is one of the first work that was done, and it's purely phenomenological distinction. This is the duration of the burst, and this is the spectral hardness ratio, which is basically the different flux into channel of a satellite. That was the first satellite to observe them, so everything is now restricted to that. And you can see that it's a bimodal distribution. There is a blob here and a blob here.
This figure is by whom?
You can find probably in the paper by Covelioku in 98. So these are go long, they last more than 2 seconds, and these are the short that last less than 2 seconds. And that's basically, it's just a pure observational distinction. When it was done, there was no physics involved. They were not separated based on any physics criteria. There was just a bimodal distribution, you have to fit it, you have to put a threshold, and that was set as 2 seconds.
All the observations with the same satellite?
This is all Bucci observation, yes. And what came out pretty soon was that the bulk of the population of long were associated with supernovae. So the evidence is now that long gamma ray bursts are associated with supernovae, while short gamma ray bursts are actually associated with merger. That was the key idea. And the distinction came from this region. There were events of
Merge of what?
merger, two neutron star or a neutron star and a black hole. So the distinction was mostly from this region, because there were few event observers belonging to this population, which had a clear associated supernova, seen in coincidence and seen evolving simultaneously. And that established the relation. On top of which, long gamma ray bursts are usually found in galaxies that are star forming, which means that there is a correlation between star formation and gamma ray bursts, which means correlation between supernovae and gamma ray bursts. And the second point is that for those cases where you can actually look where in the galaxy the gamma ray burst is going on, they are usually concentrated toward the central region, the place where star formation is going on. For short gamma ray bursts, there's a different pictures. So they're not just different in times, they're also different in population. First, in general, they happen in what's called field galaxy. So there is no preference for star formation versus elliptical versus spiral or so on. And they tend to actually happen in systems in places that are far from the galactic center. In general, these happen at a typical radius of a few kiloparsecs from the galactic center. These goes about 8 to 10, 15 kiloparsecs. This was the indication that these were probably an older population, and these represented younger stars. So if there's an older population, how do you get one of these events with an older population? There were various ideas, essentially all involved, all the time, and the key idea was actually to have it as a binary systems, two neutron stars merging, one on top of the other. Also because the merger of neutron stars gives you actually the correct time scale. And I will go back to this. So this was all nice and clear, and the distinction was pretty obvious, different population with a different physical parameter. But as you know, the things don't work out. As soon as you establish a well-defined separation between two different phenomena, there are events that happen and that fit neither. So this was one example. This is GRB of 2005. Well, what happened here is that there was a very brief spike, which is here it's not it's much higher. And that was all fine, it was sub-second, so it was clearly a short burst. But there was an extended emission lasting for 125 seconds later. The funny point is that if for some reason you just chop off the spike, and you just ask yourself what would have happened if there was no spike at all, these things would have triggered a detection, and would have triggered it as a long, because it's 125 seconds.
You also have these negative counts.
Yeah, this is how statistics work. No, I think that's actually, it's not that. So, this is 0. So there is a background subtraction. So what you are looking here is actually the counts for the background subtraction.
And the background,
So in principle, I mean, this is done such that the average of these things is 0.
Yeah. And the background comes, how much is the background?
The background appears to be significant compared to the signal.
Because of the noise you see.
Because the noise is almost...
No, the signal is 0, right?
Mm-hmm.
So, okay, this is the signal that you get here. And this is the noise. Yes, it's 1 sigma.
The background is comparable to the
Yeah.
stuff after the signal.
It's the signal to noise is 1. I agree with you. But the point is that it's not much the signal to noise, that however, if you integrate this, you get a number, you get a lot of counts.
A large excess of counts.
Yes. So there is so this kind of extended emission has this characteristic. There is an initial spike, and there is later activity. And you can ask yourself how many of the short gamma bursts have these kinds of features. And this is a plot that show again the duration of the burst. So this is 2 seconds is here. Okay, so these are all short, they're all classified as short. And this is the hardness ratio. It's the same plot that I was showing before, but just sub-selected for the short. So all the open diamonds all have extended emission. All the closed ones have no evidence of extended emission. So what happens is that about 1/4 to 1/2 of all short gamma bursts have these kinds of tail that follow that. So these are other examples. Okay, this is a collection of events for which there is a good follow-up. And here you can see quite easily. So you have all of these. I have this beautiful spike that sits in the center, the initial spike. And this is definitely sub a millisecond, because this is 10 seconds, so it's really, really short. Sub-second, sorry. Then you have the late activity. And you can see this bump here. This is quite evident. This is actually with a large temporal pinning. But if you look at a low, much finer temporal resolution, you will see variability on very small time scale.
So there's a
So-
spike, then a return to background. and-
Yes, there is also in the middle a loop
And
of
is that
emission.
fully return to background?
It's hard to say. In some cases, yes, like in this. In some cases, not really.
And does the quality of observation suggest you're missing some of the extended emission or not?
It's all the same. So the extended emission is actually slightly softer than the spike to begin with, and ultimately you still have a background. So if once it goes below background, there's no chance.
I'm just curious, like, do we think you think we're classifying all the extended emissions as extended emissions, or do we think that some of the extended emissions are being classified as just short?
No. The extended emission will never be classified as short. It might be classified as long if you miss the short phase, which is rare because the trigger will still be triggered by the short spike, unless you have suppressed the spike. If you manage somehow the physics to suppress the spike, this will be a long.
But you will never miss the extended curve.
No, it depends, but for these events, it's very hard. You have to look with the right instrument. If you look with an instrument that is not designed for a softer band, then you will miss it. So, and the point is that the spike is usually harder than the softer. So you have to have some follow-up. If you don't do the right follow-up, you might lose it. So this is the general phenomenology. So a spike, a phase of depressed emission, and then this late activity.
And what fraction of all the GRBs actually display this behavior?
is about 1/4, 1/3 of the short. So the point is that even the extended emission has high variability. So this is not like a slow evolving light curve for something that sits far away. This is also indicates that whatever is producing this emission, it must be able to drive this short time
And
variability.
does the time variability itself change with time?
There isn't that much study into that.
So there's no study of whether or not it's an expanding shell that's...
No, it's not an expanding shell, so that's pretty sure.
Or if it's expanding, it's not expanding very much.
So this is a list of events, and to give you an example, this is actually the Z, and this is the ratio of the fluence of the extended emission over the fluence of the spike. So the fluence is the integrated energy. How much energy is in the spike versus the integrated energy. Now the point is that there are cases where, for example, this one here, the fluence of the extended emission is 32 times higher than the fluence of the spike.
You mean the integrated luminosity, yeah?
Yeah, the integrated luminosity, if you want. And range is about 2. There are events where it's, in general, the key idea is that in this extended emission there is as much energy, is not more than what it is in the initial event. So whatever drives this entire phenomena must be able to hold enough energy at later times to actually power it.
In fact, it looks like this, the E does look like it dominates.
Yes, the usually actually don't. This is another plot that actually it shows many more points which are light gray and don't show up. So there is an entire forest of very nice gray points in this region, which don't show up here. But the point is this is exactly the same diagram as I was showing you before. The hardness ratio diagrams. And so the point here are that these are short gamma ray bars without extended emission. And they sit here. These are canonical short gamma ray bars. These are short gamma ray bars with the initial spike. So if you take, they are usually classified as short because they have this short initial half-life. However, if you just take the extended emission, not the initial spike, and you just say, okay, how am I going to classify a short gamma ray bar with extended emission if I only consider the extended emission? They all go up here. And here is where all the long are.
So the invisible cloud is the cloud of long.
Yes, there is an invisible cloud, which is the cloud of long. So the result here is that the extended emission have all the properties of a long gamma ray bars to a certain extent. However, it has to take with a population that is the population of the short. Okay. And the other is, again, this is not seen very well, but there was another forest of points, but the point is in general that the X-ray afterglow at 11 hours in short gamma ray bars with extended emission is similar to the X-ray afterglow in long one, which is another evidence that whatever powers the late activity has a property which is similar to whatever power the late activity in long gamma.
It sounds like when you argue the extended emissions are in fact long ones who just happen to have a spike, rather than short ones that have.
Yes, that's exactly what I'm going to add at the end. And there is another point, is about this late engine activity. So all that I show you is that there are this class of system with extended emission. Now I want to show you another evidence for late activity in this kind of short gamma ray bars. And then I will try to recap. So we know of late activity in long gamma ray bars in the form of flare, and the fact that there is a plateau phase that is seen to last about 100 to 1,000 seconds. And now we have the exact same thing in a short bar. So this is clearly a short. There is a spike that lasts less than 1 second. So it's definitely a short. Would be classified by everybody as a short, except that in the X-ray band, at about 10 to 100 seconds after burst, there was this bump here. And don't consider the bump, it's a plateau essentially. So what happened is that this event, whatever triggered the initial spike, was able to reinject energy for about 100 seconds, 10 seconds later from the spike, and this energy showed up as a plateau phase. And this plateau is not much different than the plateau that you see in the long, in terms of duration and everything. So all of this, okay, to go back to long. All of this tells you that the extended emission looks like the long, and short gamma ray bars have late engine activity. Now the general picture of short gamma ray bars is the following. You take two beautiful neutron stars, you have them merge with each other, they form a black hole. It takes about 1 millisecond to form a black hole, because this is the typical orbital dynamical timescale in a merger of two binary neutron stars, and you create an accretion disk around. You can compute how long it takes for this accretion disk to accrete, and the typical dynamical timescale or cooling timescale or every timescale that you can think of is actually of order 1 second. So after 1 second, your system is done. You form the black hole, everything inside the black hole, and that's it. You're stuck with that. And then you have to figure out how you take out as much energy as you have done before to power emission for the next 100 seconds. So all of this point to the fact that there must be late engine activity. So what people have thought is that, well, you know, neutron stars don't really merge and form your nice accretion disk. They merge, there is material is ejected, there is about half of the material get ejected on much orbits that are very parabolic. They might come back later, you might have the second phase of accretion. All of these things are nice, but you do require some fine-tuning. You do require fine-tuning also for another reason, that the accretion torus that you form around in this black hole, it's actually very dense, and it's neutrino cooled. So at the very beginning, these things is thin and neutrino cooled. But as the density drops, neutrino cooling stops. The disk puff up, there are still nuclear reactions going on in, and basically what happens is that you blow up the disk, because it can't cool efficiently. Now you have to ask yourself, and that's put a limit of about 1 to 2 seconds to how long you can support an accretion torus around your black hole before it actually evaporates because of decay of alpha particle or neutrino heat. Now even if you have material coming back later, that will go through the same things. It will create a disk, but that disk cannot survive for 100 seconds for the same reason why the original disk couldn't survive for 100 seconds. It's a little bit, you will get too low density and you will again explode.
So the puffing up of the disk, is that because your neutrino capacity goes too high?
No, it's because you don't. So at the beginning you have density which are high enough that you can cool for neutrinos. So neutrino cooling is efficient, and your disk is basically thin.
Yes.
So there are nuclear processes inside that are heating the disk, but the disk cool efficiently. So you are losing neutrinos, but you are active. The point is that when the density drops, neutrino cooling stops. Because it's like every cooling goes like density squared. So what happens is that now you cannot cool your disk efficiently. So your thermal energy goes into heating the disk. The disk puff up, and now that you have a puffed up disk, accretion rate basically drops. And you can drive thermal wind, and basically you explode. When I say you explode the disk, is that you deposit all your energy as thermal energy, all the alpha particles that decayed, or the nuclear reaction that happened inside, deposit energy in the disk, and now the disk inflates. And so you stop accretion and you explode the disk.
But there's not enough energy in the exploding disk to power the extended emission.
No, I mean, there is not in the sense that there is not enough energy. So the point is that that disk, it's when you look at the few simulations that people have done, if you merge two neutron stars, usually you have about 0.1 solar masses of stuff in that disk. Now, accretion is a very efficient way of extracting energy. Nuclear reactions are not. Your disk is blown up by nuclear reaction. So you have 1 to 2 orders of magnitude less efficient energy deposition. So that also factors into how you power your things. So the things that we came out, so the idea that we have been working is that perhaps given that you have an hybrid phenomenology, so you have an initial thing that looks like a short but the rest that looks like a long, you can take an hybrid engine. So an engine that at the beginning behaved like a short but somehow managed to remain as a long one. And the key idea is that you need to have an engine that can store energy for a long time. A black hole is not a good way of doing that because it's very hard to take out energy from the black hole. But a neutron star is a rapidly rotating neutron star is a good way of storing lots of energy into rotation, and then you can tap it later. So the idea is the following. You can form probably a massive neutron star either by collapsing two low mass neutron stars or by what's called the accretion-induced collapse of a white dwarf. So it's basically what you have in supernova 1A. You accrete a white dwarf, and you know as soon as you go above 1.4 solar masses, it just collapses, and boom. You can also have a collapse in certain circumstances that goes to a neutron star instead of exploding as a 1A. So what will happen in the end is that you will have a neutron star and you will have some leftover disk. And the reason why you have a leftover disk is that there is lots of angular momentum in both of the systems. So you can't store all the angular momentum into the neutron star, you will form this. Now you take this event, will give you your spike. This has all the ingredients to provide you with the initial spike. It's a short, it's a hard, the typical time scale of accretion of this disk as of that order. However, in the meantime, this disk is heating. There is magnetic field, there can be disk wind, there is this neutrino cooling that goes on. So this disk is accreting, it's giving you your spike of emission, but it's also giving you wind. So what happens is that you can ask yourself, okay, what happened to this wind? This wind will take part of the mass of this accreting disk, let's say a 50% fraction, that's the usual amount, and they will put it into a kind of ejecta shell that surrounds it. There are many ways of getting this ejecta shell. You can get it either directly from the collapse, the material flying out a large distance, either through MHD wind, or by neutrino-driven heating of the disk. So now you are left, now you are here, okay? Now this phase of accretion initially gives you a spike cease, because the disk has gone, has evaporated. And so you have this lull in this phase C. And also you have this ejecta shell that's propagating out with a velocity which is about 0.1 c, this is the typical entropy of the system, and a mass which is about 10 to the minus 2 to 10 to the minus 3 solar masses.
So are you imagining that the shell is in fact blocking line of sight to the central object?
Well, no, it doesn't matter. What matters is that there is no more accretion, so this thing is not giving you anything. What?
Would the shell have enough emission in some band that you could...
Yes, in optical. There are mini-nova, these are called mini-nova, the equivalent of this. The point is that you have a neutron star here now. This neutron star is rapidly rotating. It has probably, if it has a strong magnetic field, it will have also a strong wind. And now you can take the model that's been developed for a long duration gamma ray burst with the neutron star, and look what will happen. Well, it will happen exactly the same things. It will power a long duration gamma ray burst. It will power a long duration gamma ray burst inside this shell, and this long duration gamma ray burst is actually what it gives you the extended emission, which looks like a long duration gamma ray burst because it's powered by a similar energy. So you just have to look at this. So there was a work done by Brian Metzger and the other people in Berkeley that looked at the typical energetic and time scale, and it looks fine. There was still the problems of getting the collimation. So gamma ray bursts are collimated. So if you don't put this shell around, okay, you can still get this phenomenology because you can still stop the disk from accreting and then use it in. But the problem is that you will get a jet in this direction for the spike, and you will get a pulsar wind which is mostly equatorial. So you have a geometrical problem that if you are in a configuration where you are able to see the spike because you are face on with the jet, you will be edge on with respect to the disk. You shouldn't be able to see the extended emission. If you are edge on with the disk, so to see the extended emission, the jet is pointing perpendicular to you, you shouldn't be able to see the jet. So you have to figure out a way to actually recollimate this late emission, and that's what we have done with this simulation.
So did you really say accretion, excretion along the disk? No.
So, no, the point is this.
Right?
So at the beginning, the jet is along the rotation axis of the pulsar. But later, when the disk is finished, and you just have the pulsar wind, the pulsar wind is equatorially dominated. So most of the energy goes into the equator. It's like the solar wind, if you want. Most of the energy is in magnetic field. So it goes like.
No, the wind. Maybe it's mass loading, but the speed, of course, is.
The speed is different, but you have to look at the energetics. So most of the energy in the pulsar wind goes onto the equator because it's a force-free wind. The result is that if you want to see the jet, you have to be aligned with this because there are Doppler boosting. So you can only see it if you are aligned with it.
Yes.
If you want to see the extended emission, you will have to be aligned with the equator. You can't be aligned with both in any system. So how you can recollimate the things? So here is what we did. So you take your ISM, which is a ball. This is exactly the same pattern I use for long bars in every single. I only change the name of the layer. There is an outgoing shell, which is this shell of ejecta, that moves at this typical speed and has created a cavity inside. And inside this cavity, there is.
So do you mean VSN 0.2 to 0.1C or 0.02 to 0.1C?
0.2 to 0.1 to 0.2C, yes, the wrong way. But the point is that the wind from the pulsar is a much higher speed. It's a typical speed of light. So you form this kind of nebula because this wind has to slow down somehow. And there is enough mass, even if it's 0.1 solar masses, there's still enough mass here to provide you with some inertia. And the result is that if you have also a toroidal field, you will drive a jet because of the structure of the pressure that forms in this nebula, because of essentially the hoop stresses and the magnetic tension. And these are the results. So here is the density, and here is the velocity. So there are three different cases, and they depend on the ratio of the pulsar luminosity over the mass of the ejecta. So what happens is that the system is self-similar, essentially. The only parameter that really regulates the behavior is what is the luminosity of your wind versus the mass in the ejecta. And I think I have here the results. So this is for a low luminosity case, which means that L over M is 10 to the 50 erg per second per solar mass. And these are high luminosity cases, 10 to the 52 erg per second per solar mass. So what are the differences? First, if you look at how the shell is structured, there are models for this shell, you will see that the density is much higher in the interior and it drops down. It goes like the radius to the -4 or to the -2. So most of the confinement is actually done at a very small radii. Once you break through, you actually emerge quite easily. The other result is that there are changes in the way this outflow is collimated. So you can see that you get a decently collimated outflow in the low luminosity case, but you get an outflow that is actually flaring out. So it's a very large opening angle in the high luminosity case. There is also a limit, as you can see here, above which essentially if you take a pulsar or a protomagnet which is too luminous, you are just blowing out the entire shell, so there will be no confinement at all.
Is there an ambient field?
No, so there is only the pulsar which is producing its own field by spinning inside. And the other thing is that if you actually go to a luminosity which is below this Vedas, you basically have a choked jet. So you will create a jet, but the jet will slowly move inside your star, and it will not emerge fast enough for to actually have this system work. It will take too long for the jet to get out. So, basic results. So these are the scaling. Okay, these are the scaling in terms of, this is E dot over M ejecta, over jet opening angle and breakout time. So what you see here is that when the energy is large, the jet opening angle, yes, that's correct. So when the energy is large, the jet opening angle is pretty large, about 40 degrees. And when the energy is small, the jet opening angle is actually small, around 5 degrees. And if you look instead at the breakout times, you will see that when the energy is small, the breakout time is around 10 seconds, and for high energy is around 1 second. This is actually this ratio, an energy to the -2. So what happens is that you can ask yourself, okay, how weak can this event be before I get to a breakout time which is 100 seconds? So comparable to the duration of the event, it means it doesn't work. So if you extrapolate around here, you will get that by taking an energy which is about 1.5 order of magnitude below the minimum that we did in our simulation, you should have a choked jet. You can rescale that for the case of the long, and you find similar numbers that have been found in the case of the long. There is some rescaling that has to be done. The other things to show here is there's a triangle here. So this triangle were done for cases where the mass in the shell was not uniform, but was essentially concentrated into the equator. There is this idea that if you evaporated this, most of your evaporated matter should actually be on the equator, and the pole should have less density. What we found is that in general, what really counts for the jet angle and the breakout time is not the total mass in the ejecta, but an effective mass corresponding to the density that you have in the polar region eventually. So these, for example, had a lower density in the polar region, and as such, they correspond to cases with a lower average mass in the ejecta.
So, the lower part of the plot, or the second, that's the duration you said?
That's the breakout time, the time to take for the jet to emerge out of the star.
Yes. And
It's not the duration.
and is that, I mean, it just seems to be connected to the opening angle.
It is. It is.
Power means faster breakout and less collimation.
Yes. More power means
Yeah.
faster breakout and less collimation.
So you're saying is if you put a highly anisotropic amount of mass, you can maybe get 100-second duration.
Well, if you don't put any mass on the pole, basically
If you don't
there's
put any
no
mass on
stopping.
the pole, then you can't give your 100 seconds without choking the jet.
If you don't put any mass on the pole, you will get 100 seconds, but you will get something that's very open. That's the point. because it corresponds to having a very high luminosity. So no, so this is not the duration, this is the breakout time, how much it takes for the jet to break. So this is instead the so-called isotropic luminosity. So the isotropic luminosity, you get it when you take your jet, you know how much energy goes into the jet, and you correct for the beam. So two jets that have exactly the same total energy, if one is more beamed away you, it has a higher isotropic luminosity. So what you find here is quite interesting, because the opening angle increases with the energetics of the systems. So it's true that you put more energy with a stronger wind, but you also get a wider jet. So at the end of the day, even if you change your luminosity by 2 orders of magnitude in this system, the net isotropic luminosity is more or less constant, within a factor of most 3. And this is only a function, at the end, of the mass of the ejector, which tells you that if you want to have something that have basically a lower isotropic luminosity, you will have to lower the mass of the ejector, and vice versa. Because the pulsar regulate themselves. If you put a pulsar which is brighter, it will make it larger, and the two things will compensate. The other thing is that we can try to estimate what is the mass in the ejector that you need to actually produce the ejected emission that you produce. So this is the typical isotropic luminosity of the jet when it emerges out of the star, and is derived from this plot. And this is the typical mass in the ejector. There are a few corrections that have to be done. There is one correction, which is the radiative efficiency, because this is the total energy, and you have to convert into radiation. There is another correction, which is essentially due to the fact that what sets the opening angle is the initial luminosity of the wind, the luminosity during the breakout phase. What sets the luminosity of the extended emission in the luminosity after that, once it has broken out. And a magnetar will spin down in the meantime. So the two are not the same. It will put more energy into opening this channel, and then it will slightly fade as it produces the extended emission. So there is a ratio between these two, which is about 3 to 10. So this is 0.1, this factor here. And this is the typical luminosity of the extended emission, which in general is of order 10 to the 49 erg per second. And you find that for these typical values, you get 10 to the minus 2, a few 10 to the minus 2 solar masses in the ejector, which is exactly what you would expect from evaporating disk left over from accretion or merger or things like that. So this is the magnetar spin down. Oh, review the point. So what you can do at this point is, okay, you have your model. You know what is the jet opening angle. You know the typical time. You know you can correct for this effect. So you can take what we did. We took the model that we had developed before, which give us the spin down of a magnetar. And this is just a model for the magnetar wind, and try to see under which condition, if you take this kind of light curve and this kind of spin down curves, you can get the light curve that we get. And here is what we got. So these the dotted, the dashed dot, the dashed triple dotted line are 3 gamma ray bars, 3 extended emission. And here plotted, the solid and the dashed line are basically model based on our polar cap model that I've shown you before in the slide before, and then corrected for the kind of opening angle and the typical mass that we find from the simulation that I have submitted. So what the phases that we have is this. So the initial spike is not simulated here, but there are 2 reasons why we have this lull initial. One could be the fact that all your system is confined within this shell, so it hasn't emerged yet. But there is also another reason, and is that in order to get emission, you need to get optically thin, because otherwise the things will not emit anything. So the jet needs to expand to a certain distance before it becomes optically thin, and that also dictates a certain threshold for emission. And this happens to be at around 20 seconds, no matter what. Then you can see that there is a fading period. This essentially traces back to the properties of the spin down. It's slightly different between the internal shock model and the magnetic acceleration model, because depending on the efficiency with which and the radius at which these things happen. And then there is a late phase where the luminosity goes down completely at about 100 seconds. And that is essentially due to the fact that the magnetar at that time stops to work to a certain extent. It cools too much and the wind becomes electronic dominated wind. So you have a change in the physics which goes beyond. But the point is that ultimately you are able to get typical light curve which are in the right ballpark in terms both of duration, of wave shape, and of energetics that you get for this fish. And that's it, more or less. So that was the work that we did. Basically, we evaluated the geometry of the interaction. We tried to see what were the regime under which these things would work, both in terms of if you go too faint, too low energy, you will choke. If you go too high energy, you will blow up the entire shell, so you will lose the collimation. Try to figure out what was the scaling of the jet. And if once you have that kind of scaling, you actually, and you can use it with the model for your evolution of your magnetar, you do get the correct properties of the extended emission. So,
If you lose the collimation, then you have only the first spike.
if you lose the collimation, you are mostly likely to have the first spike, and you will have a very faint, probably extended emission. You might also have other phenomena, I mean, because remember that this wind is pushing at a very high speed against the shell. And so this is we haven't looked at that, but there is a chance that you could drive a nuclear reaction in the shell itself by pushing with the high-speed wind against it. So you are driving a new supernova inside the shell. And that could give you some signature in terms in the optical, again, one of these mini novae things that people have been working while trying to
So there is some chance of assuming this model works and trying to characterize.
So the model is kind of iffy in the sense that, for example, you require magneta which are not too luminous. While for the long duration gamma ray bursts, you require magneta which are very strong. And there is a reason for that. You have lots of masses, you have 10 solar masses of stuff confining you, and the long gamma ray bursts are in general more energetic. These are the less energy, you have also less mass. So if I put the same magnet that I give along, I put inside here, it will basically blow the entire shell apart, like the shell wasn't even there at the beginning. And the entire systems wouldn't look like that anymore. I mean, we'll have to find another. You wouldn't get the standard emission as a collimated things, for example.
Well, would you be able to see it at all?
You might be able to see, but if it's not collimated, you lose lots of the fine. You have to explain why you get this very high variability, for example. Why it doesn't get washed out completely. Because I mean, so there's a difference between being on line of sight with the events or just having to look at some integrated emission that comes from side lobes of things that are emission. So there are these problems. And the other is that will also means that your extended emission, which is 30 times higher than the fluence, is actually way higher than the fluence. And that gives you a major problems because now you have, for example, that, okay, I had to accrete 1 solar mass of stuff or 0.1 solar mass of stuff to give me the spike. And then I have to accrete 3 solar mass of stuff to give me the extended emission. How do I do that in the merger? So that was mostly the point.
Tightly spread one of them.
Yeah, but why? Yeah, but you mean you have in the merger scenario there are constant. In the long you have more leverage. In the long there is not. I mean you can make a 2 solar mass black hole, but it's something else. A 3 solar mass black hole, a 4 solar mass black hole. You have 10 solar mass of stuff to plunge inside. A neutron star is 1.4 solar masses. You can do a 3 solar mass black hole. It's quite hard to find a 5 solar mass black hole from 2 solar masses.
Come on, Jeff. You have 2 neutron stars in a red giant.
But then the time scale would be way too long for that. That I know, that's the Zhukov object, or how it's called it, things. The Novikov Zhukov object, how it's called that. It's the neutron star that orbits inside a red giant. I thought there was that. There's an object which is called Novikov object, which is, people think is, a neutron star orbiting inside a red giant.
Right inside, you mean inside?
Well, a giant is a bit of a problem to defining the surface of a red giant, but let's say inside a red giant.
Pretty high drag, right?
Hmm?
Pretty high drag.
Yes, but it's still a neutron star.
Yeah, well, I mean, it will slow down. I mean.
Yeah, in fact, the idea is that it's slowly drifting down to the nucleus.
Those neutron stars do not have a very high mass to cross section ratio.
Hmm?
Neutron stars have a very high
No.
mass to cross section.
Yeah, and the red giant basically vacuum in the external lattice.
So has there been other proposals for the external emission?
So in general, the key idea is that it's late phase accretion. So, and it's late phase accretion from matter put in highly eccentric orbit. So the idea is that, well, you can merge to a neutron star and you can have about, you form your black hole and you form an accretion disk, which is basically half of the mass, which is, you will make unbound about the same amount of mass that you can have in the accretion disk, depending on the geometry of the interaction. So you will form this disk, plus you will throw some matter. The question is that nobody is really able to tell if this matter is unbound or not. And the reason is that you cannot follow this matter in simulation, because you don't have the space to follow them. And because there is lots of physical process going on. So this mass is heating because of nuclear reaction rate, is cooling because of neutrino. So if it is bound or not depends also on that. I mean, if it cools sufficiently, probably it will go back. But if it doesn't and it inflates and it heats up, then it might get unbound. So you might release enough nuclear energy inside this blob of matter to make them unbound.
So that is a competing model, you mean?
That is the competing idea. The point is that it's not very predictable. Because if you want a 100-second burst, you have to say, okay, I just need to put enough mass in an eccentric orbit so that I have a stream of matter feeding back over 100 seconds. But it doesn't allow you much. And I don't think it has been worked out in detail because it's hard to redo. But in principle, it's possible that you have something like that. You need to have a way of storing energy. So it's either you put your mass far away and you reaccrete later, or you have to store in some other form. And the problem is that even if your black hole is rapidly rotating, if there is no disk around, there's no way of extracting that energy because it can support the magnetic field. So that's the only idea that has been put forward. But there are other things like this plateau that is observed in these short bursts, which people have say could be the indication of a magnet. It might not be a long duration magnet. So you have to remember this. In principle, you can, for example, form an hypermassive neutron star, which is supported, for example, by a differential rotation. Then that system will slow down, and at a certain point it might collapse with that. So it doesn't. The magnet doesn't have to survive for ages. If it survives for 10 seconds or 20 seconds, it might be enough to give some of the late energy activity. So you might have these systems that basically is supported by excess rotation, and we don't know what is actually the limiting mass of a neutron star. I mean, there was even on an Astro PH, I think last year, there was a paper about this 2 solar mass neutron star, which is at the very edge of the limiting mass that you can get. But these are still old systems. You don't know when it's young, it's formed, it's hot, it's viscous, it has neutrino, it has also differential rotation. Maybe you can support mass which are much higher for 10, 20 seconds before they completely collapse down. The time scale are a bit long because the typical sound processing times are small, but it depends on the heating and things like that.
Any other questions?
True, like this is, I have no,
Yeah,
no intuition when everything's relativistic.
No, but this the only relativistic things here is that the speed, basically.
All right, so if there are no further questions, then let's thank you very much. And that was then the last activity of the summer. It's already late in